Hi, good morning, good afternoon, and good evening, everyone. I'm so excited to welcome all of you again at our next session of AI 42, where our amazing speaker, Terry, is going to give us a great introduction about how to use advanced analytics on Databricks. So let's welcome our speakers on stage.
Hello, Terry.
Hello.
Hi, Terry. How are you?
I'm good, thank you. Yeah, very well. And yourselves, all good, I hope?
Yes, everything is
fine.
Good.
And just a few words about Terry. He is a Microsoft AI MVP. So his focus is on all things AI and data science. And I think he will tell a little more about himself during his session. But you know, he has a passion for applying traditional software engineering techniques to data to improve the way teams deliver machine learning projects. And we also heard that Terry has a podcast about data science. Can you tell a few words about that as well, please?
Yeah, absolutely. Yeah. So we started a podcast a while ago. It's a little infrequently updated. Hopefully, I'll update it more frequently. We actually have a new one kicking off as well soon. But the podcast we have live at the moment is called Data Science in Production, and it talks around a whole load of topics, which are all focused around that, helping data scientists understand what are the techniques that really help drive your models into production faster and more reliably, so that you can ultimately offer an ROI on what you're doing quicker.
That sounds really interesting, yes. That's cool. I can't wait to check it out. Maybe we can share a link for that later in the session. All right. Then I think it is time to talk a little bit about what is AI 42, and then we come back to you, Terry, so we can hand it over to you then.
Good stuff.
So we came with AI 42. With the motivation for starting this come from the recognition that there is no good starting materials. And AI 42 is a strong team consisting of 3 Microsoft AI MVPs that strive to provide you with a valuable series of lecture that will be helped you jumpstart from your career in data science and artificial intelligence. AI 42 aims to provide you with the necessary know-how that can help land your dream job as long as it's related to fields of data science or machine learning. The concept is simple and involves professionals from all around the globe explaining to you the underlying mathematics, statistics, probability calculation, data science, and machine learning techniques. We will guide you through. All you can have to do is to follow our channel, enjoy the content every second week, fill it with real life cases and experts' experience. Don't you worry, we all started from scratch, and we are happy to help build it up from there. You can always stop and rewind the videos or ask the clarification in the comment section. We hope to assist you on the wonderful journey and have you as a speaker one day. By creating cross collaboration with the organization, we can give the best opportunities to broaden your network in the AI and data science communities. With the combination of our offer services, we will support less fortunate people and organizations that are not that recognized yet, even though they deserve it.
Our organization is sponsored by Microsoft and Miles, and we are humbled by all the support that we get from our contributors as well. So first of all, I would like to say a big thank you to Levente Pongor, who made all our beautiful graphical content, and Mina Mari for the cool intro music before our events. We are also in close collaboration with C# Corner and Global AI Community, so our lectures are going to be available also on their YouTube channel, additionally to our own media. Nicola Toth creates and reviews all our text content we use on our website or advertisement and during our sessions as well. You can follow us on Facebook and Instagram and on Twitter as well. And you will find every information that will bring you to an advanced level in the field of AI and data science. You can watch our recorded sessions on YouTube. And if you want to find our next upcoming sessions, you can go to our meetup page. You can find all this information.
And as well, we have the code of conduct outlines, expectation for participation in our community, as well as steps for reporting unacceptable behavior. We are committed to provide a welcoming and inspiring community for all. Be friendly and patient, be welcoming, and be respectful with each other. So you can all find on our website. And now we can go back with Tere.
Hello.
Hi, it's so good to have you back. And the awesome thing about having Terry back is that finally we can hear about how to use Databricks for advanced analytics scenarios. Terry, would you like to tell a bit more about what we will hear about today?
Yeah, absolutely. So in our session today, what we're going to look at is we're going to start off with a kind of high-level overview of what Databricks is, and also how Databricks implements Apache Spark. And we'll talk a little bit about traditional analytics and what we try to solve there, and then what are some of the scenarios we want to try to solve with advanced analytics. We'll talk a bit about machine learning, a little bit about graph-based processing, and we'll have a look at some demos of both of those to kind of better understand how Spark can allow us to do all of these kind of use cases, but at scale.
Wow, that sounds really exciting. I can't wait to get started. How about you, Terry?
Definitely. Super excited. It's a topic that we love talking about. There's a lot to it. There's a lot of moving pieces. It's a lot to get your head around, but I think, when you start small and run through some of the examples, it'll all make sense.
All right. I think, Gosha, do you agree we should hand it over to Terry so he can get started?
Yes, let's start the show.
Cool. All right. Good stuff. Thanks, everybody. Thanks for having me. Very excited to be able to talk to you all about advanced analytics on the Azure Databricks platform. One thing I should say is that whilst we look at Azure Databricks, everything that we look at here will work on any one of the clouds. So Databricks is available in both in Azure and GCP and AWS. So you can run these examples anywhere. Hi, I'm Terry McCann. I run a company in the UK. We're a consultancy called Advancing Analytics, and we specialize in pretty much anything and everything data engineering or machine learning, particularly on the Microsoft Azure platform, but we dabble in GCP and AWS too. There's a picture there of the podcast, but what I'll also do very quickly is just call your attention to our YouTube channel. If you like content like this, and you'd like to know more about machine learning at scale or more about Azure Databricks, do check out our YouTube channel. We've got, I think about 150 different predominantly Spark-related videos up there. So yeah, go and have a look. But right, on to today. So I thought we'd kick off a little bit. When we think about advanced analytics, it's probably quite good to try to scope that into what we're actually kind of talking about. And we'll do that by initially talking a bit about like what is traditional analytics and how does that work? So let me bring up my whiteboard. So when we think about traditional analytics, what we're kind of thinking about here is the process of what we would typically think of as business intelligence, right? It's where you might have a database or you might have a number of different databases that you're working with, and you're looking to produce something which is optimized for analytics. And so you might take all your data or a subset of your data from those systems, and then you might go through this kind of stage process where you stage it, you clean it, you kind of transform it up until the point that you kind of present it, right? And this is a large amount of what traditional business intelligence is. And there might be multiple kind of, databases along this process. Ultimately, until you probably get to the end where you design something along the lines of what's known as a star schema, right? And this star schema is taking what used to be an online transactional system over here, an OLTP based system, over to what we call a kind of OLAP based system, an analytical engine, right? Now, we've been doing systems like this for a number of years, and everybody's kind of quite familiar with how this process works. And those kind of analytical systems are great to solve lots of problems. Now, the difficulty that we often find with systems like this is that they always look backwards, right? We are looking to say, oh, okay, something happened. Why did it happen? What can we do in terms of understanding what were the key indicators potentially that caused us to increase sales? So always looking backwards. Whereas with advanced analytics and with machine learning, we're typically looking forward, right? We're looking to say, well, based on what has previously happened, what will happen tomorrow? What can we do in terms of time series forecasting? What can we do to reduce the churn of our customers? What can we do to understand the patterns and behaviors and the connectivity between our customers and the products they buy, or our customers and their peers, right? We're looking to better understand the data that we have and kind of look forward, but generally to kind of enrich this kind of process, right? So if that was traditional kind of analytics, when we think about more advanced analytics, what are we typically looking at? So for us, what we're typically looking at when we talk about things like advanced analytics is kind of these core pillars. The first one is we're typically working at scale. And so by scale, we're talking here at significant volumes. So that could be complexity in kind of size of your data. It could be complexity in the type of data that you have. Like scale doesn't always necessarily mean lots of data. It might just mean more complex data types. It might mean very fast data. So if you're in a retail operation, you might have very fast data coming in from EPOS till systems, or it might be lots of sensor data, right? Data that comes in very quickly, which makes traditional analytics quite difficult. So we're looking at typically something that's working at scale. We're looking to do machine learning, and we're looking to do a whole variety of different machine learning topics across that data. As mentioned there, we've got streaming. And then the last one there as well is graph-based processing. So how can we go about understanding the highly connected nature of our data to better understand how our customers are behaving? And so when we look at advanced analytics, there's a number of different ways that you can implement each one of these core processes. But kind of what we want to do is focus a bit around that one in the middle there, which is Apache Spark. And so Apache Spark, if you've never seen it before, is it's not a new framework. Okay, so it is a framework. It's a framework of multiple different languages that are working in a way which is built for massively parallel processing. Okay, and so Spark has its history in trying to essentially do what Hadoop was doing, which Hadoop was always very disk based, trying to do a lot of what Hadoop was doing, but in memory. And by putting stuff in memory, it got around a lot of the kind of disk-based processing that we had with Hadoop. So while Hadoop made things a lot faster, an in-memory version of Mapreduce Spark made things significantly faster. We are now, I think, in something like the 11th year of Spark. So Spark's been around for a long time and has continually improved. And Spark is so where does Databricks come into this relationship? Databricks are the creators of Apache Spark and the key contributors to that program still. So what is Spark? How does Spark work? So Spark, as mentioned, right, is an MPP engine. It's a massively parallel processing engine. If you compare that to something like a traditional database, that's called an SMP system, a symmetric multiprocessor, which basically means it's like one single machine. The difficulty we have with one single machine is whenever we need to scale, typically we can only scale up, right? We can add more CPU, we can add more RAM, we can, put more in it, but there's a ceiling, right? We're always going to hit a ceiling of, well, we run out of disk, slots. We run out of CPU slots, RAM slots, everything, right? We scale up, there's a finite limit. And when you hit that limit, the next place to go is to scale out. But writing a system that natively scales out is really difficult. So what you want to do potentially is look at a framework like Spark, which is built to be distribution aware and takes away a lot of that kind of complexity for you. And so this slide here is an awful term from a colleague of mine, Simon Whiteley, the physical Spark architecture, right? But we'll have a look at how Spark works. So being an MPP system, it's a cluster-based processing. So in this cluster here, we've got an example where we've got a driver node and we've got 2 worker nodes. And now the driver node is ultimately responsible for telling Spark and telling all the workers what to do. And now this is a kind of very common scenario where you've got one driver and 2 workers, but you might have more, right? You might have a single driver and 4 workers. Now, depending on what you're trying to do, that scale is incredibly elastic. So it might be that actually you're saying we've got this huge task that we want to run out very quickly. And it's just huge amounts of data. And we need to chunk through all that data. Well, you could scale that number of workers, to 1,000, 2,000, 6,000, right? Whatever the scale was that you needed, you can scale to that point. And it's not uncommon to see customers with huge clusters, upwards of thousands of nodes, trying to orchestrate very complex problems. Now, it's always worth calling out that everything you see and everything you work with in Spark is built around the Java virtual machine. So Spark runs inside the JVM, which has some interesting quirks when it comes to running traditional machine learning workloads, because they're not going to scale quite in the way that you would expect, because there's always this awkward translation between Java and Python, but we won't necessarily go into too much there. So if we think a little bit about how Spark works, is ultimately we need some kind of cluster manager. Now, Spark is entirely open source. Everything that you have in Spark, if you want to, you can just run up on your laptop. You could run it up on, a server somewhere, and you can do exactly what we're going to look at in Databricks. You can run the same processing. The difficulty we have is the actual configuration of all of that way of working is very difficult. And so what Databricks does is it gives us a lot of utilities and a workspace on top of it, and ultimately makes it the easiest way possible to get started with Spark. And so we have that via Databricks. As mentioned, we've got complete elasticity with our cluster sizing. And if we want to, we can actually just say, well, I'm kind of happy with starting with 2 machines. And then what I want you to do is I want you to scale as you see fit. So if our workload increases and we find the pressure is getting too much for our cluster, actually just go ahead and scale. And I'll pay a bit more, but then hopefully the amount of time I'm waiting for training a model or for chunking through some really gnarly kind of EDA activities or some feature engineering will be heavily reduced by that scale. And then as that eases, actually then just kind of gracefully scale back down when I'm not using it and just keep going at that smaller size. So that's a great way of working. Now, the way that a lot of this works as well is, so the whole ethos behind Spark is to try to do small things, lots of small things in parallel. So there's multiple degrees of parallelism inside Spark. The first one you get is through having multiple workers. And so each one of those workers is a physical machine. Then we get additional levels of parallelism down to the individual cores on each one of those machines. So each core can work independently and chunk through your data. So if you've got a 2-node cluster, so you've got 3-node, 1 driver, 2 workers, and you've got 4 cores, you ultimately have 8 things that will be constantly working in parallel, trying to chunk through whatever problem that you have. Now, if you're working with your data in something like a HDFS-based subsystem, so a Hadoop-based subsystem such as Azure Data Lake Store in Azure, or Azure Blob Storage, or Amazon S3, all of these kind of HDFS systems, what they natively do is they will chunk up your data even smaller. So they store data into something which is known as an extent. And then what we're able to do is each one of our cores is able to read that data in parallel in these much smaller chunks. So we're able to read things in very fast, and we're able to write things out very fast. It's just, the great way of how Spark works. So typically when you write a query, your query will go to the driver, and that driver will distribute that query over to each one of the workers. Now, this is kind of where the Mapreduce operation comes in. So Mapreduce, if you've not looked at Mapreduce operations before, all they try to do is map a function to where your data is. And because your data is distributed across multiple machines, rather than bringing that all back up into the driver, doing some computation and then giving you a result back, we do the small amounts of computation on each one of our workers, and then we just aggregate the results back up. Each worker will read that data back in, do its kind of calculation. Maybe that is, summing up the number of items or trying to do some complex aggregations. They'll work out what they need to do, and then they'll give all the results back to a single worker to perform a final aggregation and then give you your result back. That's our kind of distributed way of working. So as mentioned, Databricks, what Databricks gives you on top of the kind of open source way of working is a fantastic workspace that's kind of collaborative, and we'll have a little look at that. It also gives you the Databricks runtime, which is a kind of like an environment with lots of different ways of working. So that might be if you're using Delta, or if you're using Apache Spark. You would be using Apache Spark, but if you want Mlflow and TensorFlow, and getting everything kind of combined together in a really nice way is kind of how the runtime works. It also gives you that kind of encapsulated environment, so you know exactly which versions are running. And then it's all just built to scale on top of Azure and AWS and GCP. So it's designed to be this kind of unified environment that unifies data engineering with data science and data analytics. So the assumption there is that each one of these cohorts and each one of these personas can work together in a nice kind of cohesive way. So data engineering, build out maybe your data lake and populate it with everything else that you need. And then your data science team can come and enrich that with advanced analytics. And then your data analytics team can then provide the kind of stitching between the traditional analytics and the advanced to really offer that value back to the business. So now we're going to talk today about, one, how kind of machine learning works, and then two, how does graph-based processing work? So machine learning in Databricks is an interesting topic because it's a lot lower level than maybe some other frameworks that you might have looked at in the past. And that can either typically be a kind of good thing or a bad thing for a lot of people. And what I mean by that is Databricks or rather Spark kind of wants you to work in a way that it wants to work, and it needs you to understand a lot more about machine learning than, say, a framework like XGBoost or scikit-learn might, or even things like Torch and TensorFlow. So we'll have a little look at that and try and go through it. So just a thing to call out with Spark is, as mentioned, Spark is like 11 years old now. And so over that time, it's been through a number of iterations. And you'll typically see the distinction, if you're looking at data processing, between RDDs and data frames. And RDDs are the older way of working, and data frames are the newer way of working. And so data frames are where you should get started. If you Google a problem, which we all do, right? If you Google a problem and you find a solution to that problem, what will happen is you'll inevitably find RDD-based solutions. And with those solutions, it will probably work, but it just won't work as well as a data frame implementation. Now, you have the exact same thing for machine learning. You've got the older MLlib way of working, which is very RDD based. And then you've got the SparkML way of working, which is very data frame based. Okay. And so wherever you're working in Spark, just focus on data frame based implementations. So let's think a little bit about the kind of machine learning process, right? What somebody might go through. And somebody might go through a journey a little bit like this, right? We'll talk to some source systems and we'll bring some data in. We'll do a variety of different pre-processing steps. We'll do a lot of feature engineering, right? Ending us up with some nice, clean, structured data. Now, typically, this is what's known as like 80% of machine learning, right? Going back and really trying to refine our data. And ultimately, we spend all that time really and that kind of hard work, which is a lot of fun, right? But we spend that time focused there because what we're trying to do is we're trying to boost the signal in that data and reduce the noise and create something that's going to generalize to the problem we're trying to solve. And so we'll do a lot of that. And there are ways in which we can do that, certainly with Spark, and there are techniques, and we'll maybe look at a few of them today. But there's certainly a lot more that you can look at. Then once we've got that nice clean data, we'll go into that kind of modeling phase. So we might say, I'll try, and doing some kind of classification problem here, right? And I'll look at maybe a decision tree and I'll try that and see how that works. And then I'll go, well, actually, maybe I'll try some kind of logistic regression, and maybe I'll try naive Bayes, and maybe I'll loop back to one of them and kind of see what's happening there. And I'll iterate through a number of different models. Now, Databricks has an AutoML capability, which we won't look at, but do go and check out our YouTube because we've got videos on how the AutoML in Databricks works there. Once you've got that model right, you want to tune that model, then you want to evaluate it. Have I got a good model? And then ultimately you'll want to put that live, right? And start offering value back to your business or wherever you're trying to build a model. So now the way that Spark breaks this down is with a number of key components. You've got transformers, you've got estimators, you've got pipelining, and you've got evaluators, okay? So Spark implements, Spark kind of gives you the option to implement everything as a pipeline, which is very similar to things like scikit-learn. But the way that we get to that point is through a series of transformers and estimators. Now, we'll go through a little bit about what each are and how they work. And I'll try and keep it quite quick because I never find that these slides make a great deal of sense, maybe until you actually see what's happening. But we'll have a look through, okay? So a transformer, the crux of a transformer, okay, is to take a data frame and transform it into a new data frame. So Spark is typically the way that Spark implements data frames is that data frames are immutable, okay? So whenever you try to do anything in Spark, if you create a data frame and then you make changes to it, you're just making changes in that context. Once you rerun that data frame again, it will be the same unless you physically overwrite it, okay? You can overwrite things, but generally Spark is immutable. So when we look at doing things like applying transformers, what we're doing is we're creating a new data frame and we're leaving the original untouched. So a transformer is something that you might want to do if you need to make some kind of change to your data. And now that is a change that doesn't require you to look at the data. So that might be changing the type, that might be converting something, it might be trying to normalize some data. You might be looking to try to do something to your data, okay? Typically, we'll call transform on a transformer, and one of them might look something like this, okay? This is a Regex Tokenizer, so all it does is take a corpus of text, a string of text, and try to break down every single word in there into an array of individual words, okay? And it looks a bit like this. So it says from PySpark ML, I'm going to import my Regex Tokenizer. We initialize that tokenizer. So here it just says, right, I'm going to set an input column as review, and I'm going to set an output column as tokens, and I want you to use this pattern. Now, this kind of input column, output column is typically what you'll see in both transformers and estimators, because we're looking with that data frame coming in, we're looking at a column that we're going to use as to transform, and then we've got a new data frame coming out with our new transformed column attached to it, okay? So once we've done that, we will then call transform on it, and we'll create a new data frame. And then here at the bottom, it's just displaying the top 5 results coming out of that new data frame. And so this is a process that you'll typically go through, and you'll do a lot of these, okay? And so these might be things like scaling your data. It might be, again, doing stuff like this. It might be doing a kind of count vector model where we're looking to count the number of individual tokens. Whatever you're trying to do, your feature engineering is in here, labeling, coding, one-hot encoding, etc. is going to be a combination of transformers and estimators. So then back on the estimators. So an estimator is anything that requires you to look at your data. So if you think about imputing missing values, say you've got the age of your customer, right? And you've got very sparse data. You don't know the ages of all of your customers. And you say, what I want to do is I just want to replace every missing value with the average age. That's not a very good strategy, right? But it's a strategy you might choose to take. And so if you do that, you need to look at the data and you need to first calculate the average age to then apply it. So whenever we're looking at working with an estimator, our estimator needs to see all of our data, calculate something, and be fit with that new function before applying it to the actual data. So with an estimator, you will fit an estimator with your data. And then once it's been fit, it then becomes a transformer, which you then use to transform to create a new data frame. I know what you're all thinking. That makes perfect sense. You really explained it really well. Thank you. Thank you for that. And stuff, it gets a bit complicated, but I think when you see an example, you'll get it, right? And so once you've got its estimator, this estimator becomes our transformer. A couple of examples here. The bottom example there is algorithms, right? If you're creating a decision tree, that decision tree is an estimator. It needs to look at what you're trying to train to come up with your decision tree. That's an estimator. You're going to fit it before you transform another data frame, at which point you're making predictions. Now, the way that Spark is a little bit lower level is that Spark is anticipating that the data you present to that estimator will be in a dense vector format. So because what you have to bear in mind with Spark is we're not working on a single machine. The assumption here is that we're working at scale. So when we're working at scale, we don't have one machine which is trying to create a machine learning model. We've got lots of machines all trying to create individual models and bring them back together. So there's a higher degree of complexity. What I would also say there is if you don't have a problem that requires distributing, don't look at Spark for machine learning. Look at something else. Look at actually just spinning it up locally or spinning it up on a big machine, on a data science virtual machine or something else. Only scale when you actually have a problem that requires scale. Otherwise, you just add more complexity than you need to. So we've got those two there, which are vector indexers and vector assemblers, and we'll look at those. We also have pipelines, and pipelines are used to construct everything together. So ultimately, we have dirty data coming in one end and our nice clean model coming out the other side. And then every time we see new data, it just goes through each one of those steps and gets our nice predictions at the end. And then the last one we have there is evaluators, and did we get a good process? So we're going to have a little look at an example here. So I'm going to hop over to my workspace. So this, if you've never looked at it before, is Azure Databricks. And I am in the data science workspace. What I'll do is I'll hop back over here to my notebook. And so Databricks works all in this kind of very notebook-driven way, okay? So I've got a notebook here. And what this notebook is going to do is try to do a very basic regression-based process, but using Spark, okay? So what I'm going to do first is I'm just going to import a couple of libraries that I'm only going to use to do basic data visualization and some PySpark functions. Now, the first thing that I'll do, and the first thing that I always typically try to do, right, is to have a little look at the data and see what we're working with. And we can see here, so this is the bike sharing data, which is an open data set from UCI. But this is all pre-built into Databricks. So Databricks have a number of data sets that are just always available. So if you grab hold of this notebook and you try to run it on your own instance of Databricks, it will just run all the same data as available for your machine in AWS, in Azure, in GCP. It's all the same. You have access to all of this data, okay? And what we can see is that it's a comma-separated value. It's got a header row and a few other bits and pieces in here, right? So we can write something to consume this data. And what you can see here is this kind of syntax here, which is my data frame. I'm just saying, Spark, read my data. It's got a header. Also, I want you to infer the schema. So I want you to take a look at the data, and I want you to attempt to infer what type of data it is. And that data is available at this location. Now, the reason we infer schema is because Spark is a declarative way of working. So what you'll do is whenever you write a query, you're not writing that query in, say, pure Python or pure Java. That query is going to go off to a query engine. That engine's going to interpret it, and then it's going to try and produce a plan of the best way to run it. Now, if your data set and all of your individual attributes in your data are all strings, then it's not going to know the best way to kind of work with that, and you'll end up with an inefficient plan. So we want to infer the schema or provide the schema so that we just help it out. Now, I'm going to cache this data. So Spark is in memory. And what I'm doing here is I'm actually just saying I'm going to force it into memory and I want it to stay there. Now, let's have a little look at some of this data. So if I run this display here on df.sample, and let me just actually present it properly. What you'll see here is we've got this instant, we've got date, we've got season, we've got average temperature and the normal temperature, humidity, wind speed. And then we've got this column at the end here, the count. And that's ultimately what we're trying to predict. So if we have a little better understanding of this data, we could say something like, I want to describe this data. And so describing just gives me some really high-level summary statistics. So we've got things like the count, the mean, the standard deviation, the min and the max, right? So if we look at that count, what we'll see is that we've got 18,000-ish observations. And on average, this is hourly data. So on average, every hour, there's 189 bike rentals with a standard deviation of 181. With a minimum value of 1 and a maximum value of 977. So that probably indicates that we've got some outliers here because this is a very quite tight distribution, but we've got some much larger numbers. So there might be something we need to work with here, okay? And what we can also do is run a couple of functions. That's very helpful. It doesn't particularly want to work for us. Your currently calculation column, a date type. Cool, that's fine. So basically what we're doing here is we're going to write something to loop over and show us how well correlated our data is. What it doesn't want to do is it doesn't want to work for me because I've got a date in here. Rather than correcting that, I'll skip over it. But what you've got here is this Dfstat Correlation. And all that's going to do is it's going to show you how well correlated is my data against the label that I'm trying to predict, which is count. And what this will look to show you is you've got these two columns here of casual and registered. And if you add them up, you get count. So what we do is we've got a load of label leak there. So kind of what we need to do is drop a load of that data, which we can do here. And drop that data and end up with a nice set of data that we can use to kind of produce our model. Now, I could do the most basic of feature engineering here, which is add an extra column on, which just indicates whether or not this data is in the AM or the PM. And the reason we do that, because there's a little button down here, which I can display this data as a bar chart. And I can get some very quick kind of graphics here. Now, if we actually try and change this around a little bit, so let's not look at AM and PM, but let's look at, say, something like the count, and let's break that down by the hour, okay? And confirm that. What we can see when this runs is that we can see the kind of pattern of rental, right? We've got a nice idea of that hour is a pretty key indicator. So we can see here that in the early hours of the morning, there are typically fewer rentals than there are during the kind of morning hours as people commute to work, There's a little bit of an increase throughout the day, and there's a much bigger bike rental period, presumably as people kind of cycle to the pub. And then there's a number of crashes as people cycle home slightly tipsy, and then ultimately it tails off, right? But we can kind of see this pattern. So adding the AM and PM could be quite an interesting factor to know if it was in the morning or the afternoon. For this particular model, it's not a great help, but it's useful to kind of see that stuff. Now, when it comes to splitting our data to create a training set and a test set, we've got functions in Spark for this. So we've got this data frame random split, and that will do a very similar thing. And that's creating as a training set and a testing set. So not quite as feature rich as something like scikit-learns, but it does the job for us nicely. Now, what about actually going about training our model, right? Here we're looking at a couple of PySpark ML bits. So I've got my vector assembler, my vector indexer. I've got a min-max scaler that I don't think we use. And then what we're going to do is we're going to look to create a set of feature columns, okay? So I'm going to create this feature column here by dropping off that value, which is our count, which is what we're trying to predict. And then I'm going to use this vector assembler and this vector indexer. And what they're going to do is assemble all of our features up into a nice set prior to actually training with. So this will do the conversion of each one of those columns into a vector format. And we'll have a look at what that looks like. But again, what we've got is that input column and that output column, an input column and an output column. And we just kind of keep working in this way, okay? So we'll set that all up. And then what we'll do is we'll look at another estimator here, which is our decision tree regressor. And so again, we've got our PySpark ML, but this time we're looking at a subset of our functions which relate to regression. Now, one thing to bear in mind with Spark ML is there's not a huge variety of processes and of models that you can choose from. So there's a lot, but there's not as many as if you were looking at something like scikit-learn, for example. Scikit-learn has a lot more options, but what you do have in Spark ML is enough. So we'll set that up. We'll say, I've got this decision tree regressor. Now, what we need to do is we need to look at some of the parameters that go into that model. And one of them in here is like, what are you actually trying to optimize for? Like, what is your label? What's your dependent variable? And so we just say, all right, yeah, cool. Our label is that count. And so that just sets up our model, right? Our model now knows what to do, but ultimately our model is just an estimator and it needs to be fit and transformed. And we can do that by stitching everything together in a pipeline. And so what this pipeline does here is you can see it says set stages. I want you to assemble my vector. I want you to index my vector. And then I want you to apply a decision tree to it. And so if we run that, that sets up this pipeline. And all we need to do is fit that pipeline. So fitting that pipeline is the process of training our machine learning model. And what you can see here is a number of Spark jobs were executed against the Spark engine, and that trained our model. So if we wanted to, we could have a look at kind of what's happening. And we can see here a nice visual representation of that decision tree. And we can see it's kind of, what's that, 1, 2, 3, 4, 5. It's a decision tree with a depth of 5. And we can kind of see these breakdowns here. So feature 3, if it's more or less than this value, we break it down like this and break it down like this, ultimately, until we end up with some kind of prediction like we have at the bottom here. Now, decision trees can be useful for regression analysis, but not typically, because we end up with lots of repeating values. For our example, it's probably not a very good example, but it's the example we have. I'm just going to save that model. So, whenever we train a model, we typically want to try and save that model. So we're not having to retrain it every single time. We can just use it. And then I'm going to re-import that model. I'm going to use that model then to actually score some data that it's never seen before. I'm just going to use that as transform now. So now I've got that pipeline. Every time I want to use it, I just need to re-import it. And then when I want to actually score my data, so I'm trying to do batch machine learning, for example, All I need to do is import my data, import my model, and say I just want to transform that data. And it will go through those stages of applying all of those transformations. Now, the data that we're working with here has already been feature engineered. It's already been Z ordered and mean scaled. So you'll see you've got like the humidity is 0.42. So we haven't had to do a lot of that feature engineering. But if we were doing those steps, we would just stitch that all together in that pipeline and start off with very raw categorical data and end up with our nice trained model at the end. So what you can see here as well are those individual columns, okay? So here what we've got is our raw features in that dense vector format. So it says here we've got a vector type of dense. It has a length of 11, and these are the values, okay? So we can see each one of those individual columns as an individual value. So when it was talking about feature 3, we were talking about whatever was in this particular attribute here. Okay, and then that gets constructed again and tried to be tidied up a little bit. Ultimately, to then we've got our prediction column at the end. So what we're doing here, right, is one thing you'll see is that we've got a lot of repeating values, right? 20, 60, 60, 60, 9, 9, 9, 9, 69. And the reason, right, that's happening is because we're going through that decision process. We're going through that decision tree. So we'll typically find lots of repeating values. Now, what we might want to do is evaluate it, right? And so here we've got our PySpark ML evaluator, and we've got a regression evaluator. So by default, in our regression evaluator, we've got a couple of different things. We've got evaluators for stuff like the root mean squared error, or the R squared, the coefficient of determination. And we can have a look at how well our model is performing. And so what we can see here is that this model, on average, per hour is wrong by about 108 bike rentals, which is pretty appalling, right? So there's a lot that we could do to make this model work a bit better. Typically by not using a decision tree, that will make it work a bit better as well. There's a lot more that we can do in terms of feature engineering to really get this a lot closer to reality. And you can get this data down to about 13 rentals on average being wrong with a much higher coefficient of determination. So I do recommend you download this and have a bit of a play. And so one of the last bits we've got here, we can have a look here again to see that our average, right, for this data is 189. So that we're pretty wrong at the moment, but there's some room for improvement. So machine learning in Spark, it can be very low level, especially when you have to do things in dense vectors. A lot of the times, if you're trying to do something and you're trying to do some kind of transformation to your data, and it throws you up a random error about the data types, it's probably because it's actually expecting something to be in dense vector format rather than the format that you've provided it. And so what I'll do is I'll share another script at the end of this, which will kind of guide you through a lot of those processes. Now, what I'll do is I'll quickly shift gears away from machine learning to talk a little bit about how Spark implements graph-based processing. So I do have some slides, which I'll try and go through quite quickly. So graph-based processing has a long history, which pretty much starts with the Konersberg bridge problem. And the Konersberg bridge problem originates because there was a mayor in the town of Konersberg who was looking to try to understand, could he cross each one of his bridges in his town with only crossing each bridge once. So there were 4 land masses which were intersected by 7 bridges. And this couldn't kind of be solved, and the mayor couldn't quite understand why it couldn't be solved. And what he did was approach a very prominent mathematician at the time, a chap called Leonhard Euler. I won't give you a minute. This guy, Leonhard Euler, to try and solve it. Now, Euler initially dismissed the problem, but then later kind of came back to it and had a better look at what it was trying to solve, and broke the problem down into a number of kind of key components. So what he did was kind of take this problem, right? You've got a north bank, a south bank, and 2 islands. And he broke those down into what he referred to as nodes and vertices. So we had these nodes. So each landmass became a node. And we had a number of interconnections, which were all the vertices or what we typically call in graph-based processing edges. Okay. And with each one of those, we were able to calculate the number of degrees of connectivity. So you can see on each one of those edges where you've got 5 and 3 and 3. And where you had this kind of pattern, it's an unsolvable problem. You can't cross each bridge only once in a pattern like this. The only way to kind of correct for it, to cross each one, only crossing the bridge once, would be to remove one of those bridges, which would enable you to do that. Which, removing that gives you that option. And Konersberg isn't called Konersberg anymore, but famously bombed during one of the world wars. And some of the bridges were actually destroyed and solved the Konersberg bridge problem, just not in the way that we wanted, right? But Euler took what he was looking at here and ultimately formulated a lot of this into what has now become graph theory. And so the theory of how to work with very highly connected data. Now, graph theory is largely what's become the backbone of graph-based processing, much like relational theory is for relational databases. We have graph theory for graph-based databases. And so the key things that we need to take away from that picture is that we have nodes and we have edges. And a node is an entity in our graph, and an edge is the relationship between it. Okay. So if we look at a couple of examples here, we might have something like this, right? We've got a node that's connected to another node via an edge, and it's got this arrow, and that arrow is directed. And that's super important for us because that directional aspect is very important. The connection is from A to B, not from B back to A. You might have bidirectional graphs, but we don't in this example, okay? And so moving on, examples of that, right, might be something like a person acted in a movie, yeah? So that could be someone like Robin Williams acted in the film Jumanji, or it could be a person directed a movie. And so what we're able to do is add properties to our edges to start building up a picture of how things are connected. So that could be something like James Cameron directed the film Titanic, right? And then there could be something like this, right? A user rated a movie. And so that user might be Ash, and Ash rated the movie Alien a 9. So each of these properties is giving strength and provenance to why they are connected. And that might be something like somebody liking a film, or it might be somebody liking a book, or it might be a social network where you are friends, but then you're also friends, but then also you appear in so many photos with that person and you've had so many different interactions, and we're able to build up more and more strength between why you are connected. And graph-based processing gives us the ability to solve a huge number of different problems. Those problems are typically kind of broken down into one of 3 subsets, which might be you're trying to find the shortest path between 2 nodes. So that might be myself and yourself, and I'm trying to work out, let's say if you're on LinkedIn, how many connections is it to go between myself and yourself? How many people are we connected? The kind of 7 degrees of separation, or whatever it is, a 7 degrees of Kevin Bacon. How many people do you need to step between before you can reach Kevin Bacon, right? It might be transitive closure, which is trying to say, starting here, what I want to do is I want to find all of the people that are n hops away from me. If you're on LinkedIn, again, LinkedIn's a great example of a network graph. If you look at connections, right, you can scroll and it will say these people are recommended suggestions, because we look at your first degree connections and we look at the secondary connections that are most likely to be relevant to you. And if you keep scrolling, you keep scrolling, you keep scrolling, what it essentially is doing is traversing further and further and further out in that network to keep suggesting you more and more people that you might be recommended to be connected with through those existing connections you have. You just keep scrolling, so just going further and further and further out. And then the last one on here is polymorphism, which is to say, are 2 nodes connected? To find any connection between all of these different nodes. And that can be used to solve a huge variety of different problems. Now, some of those problems might be something like this, social graphs, trying to find who is a queen bee in a network. So typically you'll find where where it might be a particular platform. If somebody is very popular on Facebook and they've brought all of their friends over to Facebook, if they then leave Facebook and join, I don't know, some other social network, they might find that actually, because those connections are made around that subset of people, if that person leaves, that group might also leave with them. We need to try to understand who are the queen bees in that relationship. It might be fraud detection, right? Organized fraud is very hard to find. And typically fraudsters will create people that look like real people based on aspects of somebody's identity. And they might use your social security number and then your phone number and someone else's address and someone else's account details or something, and bring them all together to make somebody who looks like a real person. And understanding where each one of those slightly, so if you have a suspicious card, what is the network of that suspicious card? Well, actually, that is connected in this way, in this way, in this way. We're able to capture fraud a lot faster. It could be recommendations, right? You buy this book, your friend buys this book, maybe you'll also like this book, right? All based around this concept of triadic closure. We make triangles in a graph, okay? Or it could be used for network and IT. Again, super useful for understanding where you've got dependencies. Anywhere you have very highly connected data, graph-based processing is great for that. So what I'm going to do is quickly hop over to a different example and just run you through the first couple of slides. Now, Spark implements machine learning as just part of its way of working. It also implements a thing called graph frames. So this is a subset of how you work with data frames specifically designed around graph-based processing. So what I can do is I can just say, well, from graph frames, import everything, and I can start working in a graph-based way. So what I've got here is some data, and my data for Spark to work for graph always needs to be in vertices and edges, okay? So nodes and edges. And what I've got here is a typical example, right, of a social network. So I've got Alice, Bob, Charlie, and what you can see here is that Alice and Bob are friends, okay? And Bob and Charlie, Bob follows Charlie, but they're not friends, right? They just have a follow relationship, okay? And what we can do is we can create a graph. Now, Spark implements graph in a way that's known as an analytical graph. So it's a graph that you populate at a particular point in time, hold in memory, and then do your calculations on. It's not a persisted graph such as you would get from a platform like Neo4j or a Tiger Graph or Cosmos DB. It is just an analytical graph, okay? But you can start doing some interesting things with it, okay? So we'll just set that up. And what I'm going to do here is I'm going to say, I just want you to make me a graph. And we can display our vertices. And we get a nice list of all of our nodes. And we can display our edges. Now, what we might want to do is start working out, you know, how are people connected? How are these relationships being established? So we might say, what I want to do is I want to have a look and I want to know how many incoming degrees there are. So when we looked at that picture of the kind of Konersberg problem, we looked at all of the degrees. And this kind of gives you an example of how you could do a very similar thing to understand how connected people are. So looking potentially at who are our kind of queen bees in this relationship. We can have a look at the outgoing degrees, or we can just have a look at all degrees, so incoming or outgoing, and start to see who is particularly popular in our network. Then we might want to start doing some other kind of calculations here. We can do normal things like grouping and aggregating to try to find what's happening. But really, the power of where Spark's graph-based processing comes in is when we start looking at motif finding, okay, and using a motif way of working. And so what we have here is a ASCII art way of drawing a relationship, okay? And what this is doing is it's saying you've got this kind of brackets around here to show that it's a node traveling through an edge to another node, and then from that node back, okay? So what we're looking to do here is we're looking to say, I want to find everybody in my graph who is in some way connected to each other. So it doesn't matter what the relationship is. If you are friends and you're friends back, or you are in a friendship and you follow each other, how is that relationship? Okay. So what we can see here is we've got Charlie, and Charlie's relationship is that he follows Bob, and Bob follows Charlie back. Okay, and we can kind of traverse back through this and see where we are connected. And we could do some other filtering in here. Now, Spark Graph enables you to do a lot of very interesting things here. So what we're trying to ultimately achieve with a platform like Spark is to be able to say, well, what I want to do is I want to do data processing at scale. I then want to push that off to my machine learning models, and I want to train a model. Then once I've trained that, I want to then fully understand the highly connected nature between my audiences so that I can better target them in some way or another. And so having this all in one kind of unified platform gives us a huge amount of flexibility. There's a lot more in this, which I recommend you have a look through. But what I'll do is finish there and just say, we'll move on to answer any questions, and just say that Apache Spark is great for many analytical problems, right? Where your data's in the cloud is always our kind of go-to for batch machine learning. And when you add on scaling and streaming and graph-based processing, it's a really powerful tool to have in your data science toolbox. But always be aware that if you don't have a problem that requires scale, then typically the complexities that you get with Databricks can be a bit too much. And it's sometimes better to just focus on one single machine. My details are there. If you have any questions, do please get in contact with me. I love talking about this stuff. So yeah, just give me a shout. With that, I will hand back over and we can answer any questions.
So, Terry, that was such an amazing session. Thank you a lot.
You're welcome. It's a lot of fun.
It was nice to see how this graphing works, for example. This
Good
is
stuff.
Cool. Mm-hmm. And we have a lot of questions to you. Gosha, would you like to read them up?
Yes, so we have one question from Gabriel. Is Azure Databricks a good platform to perform advanced analytics on streaming data?
Good question. So yeah, absolutely. So streaming's an interesting one. It kind of depends on what you're doing and what your scale is as to whether or not you want to use it. But it is a very good platform for streaming. So if you take the example we touched on around EPOS till data, so Spark implements a process known as structured streaming, and that structured streaming can just hook into a streaming source, such as something like Kafka or event hubs or service buses or something like this, right? Some kind of messaging queue system. And as those come in, it implements a micro batch way of working. So it micro batches that streaming data. And if you've got a machine learning model, say, I don't know, doing some kind of churn or like trying to work out, if there's on-demand fraud detection, as long as what you're doing is kind of feeding another system, then it's a great option for doing that. If your processes require you to be 100% online, so you've got a system which is kind of producing the parameters that you're sending to your model, and then it's going to wait and expect a result back. For that kind of scenario, using Databricks probably isn't the right idea, just purely because the latency required to take your data, then distribute it amongst the cluster, do your calculation, and then return it back can typically be too long and can cause delays in your systems. So for batch and kind of streaming micro batch processes, Databricks is amazing. But for real time and pure real time, we always recommend a different kind of architecture. Good question, though.
Thank you for the good answer. So we have a lot of questions tonight. Let's see the next one.
Yeah, so another question is, can you apply pre-trained machine learning models to your data in Azure Databricks?
So depends on what you want. So there are no kind of out of the box Spark ML pre-trained models. There are a number of third parties who do provide pre-trained models, one for just for use, such as like cognitive services, and others that you can use for transfer learning. So there's a great project from a company called John Snow Labs, And John Snow Labs are kind of the pre-trained model where you'll want to go if you're looking for a pre-trained model. So if you think about something like natural language processing for health, the way that health professionals write natural language is not very natural, right? They write things like, this patient shows signs of headaches, but doesn't have nosebleeds and doesn't have this and this and this and this. So for a normal natural language model, you might just pull out the key symptoms, right, of nosebleeds and headaches and go, all right, this person's got this particular condition potentially. But you miss a lot of the negation. And that's quite a tricky problem to solve. But you can then just look at something like John Snow Labs to go and get that immediately for you. The other thing that you have as well is if you're in Azure, you've got all of the kind of cognitive services, and being able to call those services over a large data set can typically take a long time. But because we've got scale, if you've got, say, a 4-node machine, and on each, 4-node machine, and on each one of those nodes, you've got like 8 workers, then you're able to do everything at, what's that, 8, 16, 32. So you've got everything working at a 32 times scale. And each one of those can then call each one of those cognitive services at the same time and get you a much higher throughput. So there are no pre-trained models out of the box, but there's certainly a lot that you can take advantage of. And there's nothing to stop you from using any other library, such as like, PyTorch or FastAI, and taking advantage of things like deep neural network training. It's just a lot trickier to get that stuff to scale neatly across Apache Spark.
Yeah. Thank you, Terry. And thank you for the great question, Gabriel, again. Okay, so next question.
So next one is from us. So what do you see as limitation when you offer Databricks as a solution to your customers to solve advanced analytics tasks?
Yeah, great question, right? So it isn't a perfect tool, by any means. I think a lot of the limitations come around that Spark has historically been very difficult to implement. So one of the limitations is that actually it's a difficult skill to acquire. The market isn't flush with people who know Spark. An interesting thing about that is in the Stack Overflow, the most recent Stack Overflow study, they look at individual frameworks, they look at web frameworks and data frameworks, and they look at how much each framework contributed to your salary. And Apache Spark actually came out as the highest contributor for a single kind of data-related framework. So learning Spark is a great way to ultimately earn you more money, anybody watching. But it's a lot harder to find good, skilled people. It's also a lot harder to get things to work the way that you would want them to work. So for big data, Spark and Databricks is fantastic, right? When you have so much data and you need that scale, it's a great problem. It's a great tool to solve that problem. Where you have small data, typically small data queries, although they're being massively optimized at the moment by Databricks, small queries will run better on a transactional database system because it's just designed for that. So you'll never get super low latency responses. You'll always get a delay because your data is being distributed. It might be being shuffled around to do aggregations. Where you have distributions, you get complexity. And understanding why you have performance problems is very hard in a distributed system. And you typically need to know quite a lot of like low level Spark to really understand that. So it's not right for everybody. But as people's data scales, it's a great system to scale with them.
Yes, thank you. It is actually a big question when it comes to customers because, for example, I had a customer when they were working with C# and mostly Python if it was something with data, and then they totally switched over to PySpark instead, and then they literally sent their people to learn these tools and this new language, and so yes, so it's important to make a decision, I think.
Yeah, it definitely is. And a lot of, because it's also a Java-based process, there's a lot of stuff that you might expect to work, especially if you're very familiar with data processing and say something like pandas. that when you translate that to Spark, just doesn't natively scale. There are ways to make things scale, and there are ways to make things only work on the driver. And if you're very new to it, we typically see a lot of the time people, trying to scale things really big because they expect it to go faster, and they're not seeing the performance improvements that come with the cost. And typically it's because the data and the way of working hasn't necessarily been understood well enough. But yeah, it's a good thing to learn. Certainly, it's like a really great framework.
Yes, definitely. Shall we get our next question?
Yes, sure. So how to deploy Databricks notebook through different environments?
Good question. So yeah, so Databricks is all kind of based around this notion of a workspace, right? So we looked at the workspace then, and you'll typically have multiple workspaces per environment. So you might have a dev environment where you've got a workspace, a test, and a production, right? And you might even have multiple workspaces in there for different scenarios. Now, typically, migrating from one to another was always a challenge. But they've done a lot of stuff recently to introduce version control and source control actually into the product itself. So if you've got a repo full of notebooks that you're working with, then you can work with them directly, and you've got a normal kind of process of committing that and creating pull requests and merging in your changes and working collaboratively that way. So that as you commit those, they just go back into your normal kind of DevOps process, and then they'll get migrated and tested as you would with any other kind of code item. Prior to that happening, we used to have to export everything and then store it, version it to push it all through in a nice way to get that. But with the kind of repo functionality, it's become a lot easier. Again, on our YouTube, we've got loads of videos. I think Sai did a video a couple of days ago because they've completely overhauled how that process works. And it just makes things a lot simpler now. But yeah, that's a really good point.
Thank you, Terry. We have one more question. Can we take that?
Yeah, so it will be the last question for today. Can you integrate version control to Azure Databricks to manage different version experiments of your machine learning project?
Yes. So I'd say very kind of along the same lines as the last one. For versioning your machine learning, like the actual code, we've got the kind of repo functionality. But for which I think maybe the crux of what you're trying to achieve there is we also have for kind of model management and ML ops. You've got built into Databricks Mlflow, which is a managed version of Mlflow. So Mlflow is an open source tool, and they have a managed version of it. And what that enables you to do is, with a couple of additional lines of code, is to automatically track what you're doing. So in that one of the first slides we looked at saying I might try a naive Bayes and a decision tree and a logistic regression, right? And I might not actually commit every time I'm doing this. And I might find a really great first model, and then I try and improve it. And then as all things happen, right, what I do is I start off quite well because the gut's pretty good. And then I just continue to make worse improvements. I might want to get back to that original one. If I haven't committed each time, I rarely do. I'm not that, not that dogmatic about it. It might get lost. But with Mlflow, we have Mlflow constantly tracking our model improvements. And so that all goes off into a separate screen, and you can see, well, when you tried this parameter set, you got this particular score. And then when you tried this model and this set, you got this score. And when you've done that 100 times and you go, actually, I want to go back to the third one, you just click a button and then it will take you straight back into that notebook with the exact code. And then you can say, yeah, this is what I want, and I'm going to go ahead with that. But also it gives you the justification when someone says, what have you been doing all day? And you go, haha, look at this, right? I've tried all of these different things. And then they're like, cool. Which one's best? Like the first one, always the first one.
Yes, that's cool. Yeah, so thank you, Terry. It was very informative, and we again learned a lot of things today, I think. And I can talk for the audience as well, probably. And we would like you to stay for a little bit so we can tell a few words about what is coming next.
Yes.
Perfect.
So let's switch over to our slides, and then So we are back already. And Terry, thank you a lot again for the session today. It was really cool.
Welcome.
And it's not over yet this year. We are coming back with 2 more sessions, which is going to be on the 1st of December. Laila is coming to talk about Azure Machine Learning, which is one of my favorite topics, to be honest. Sorry, Terry, but this is something that is the one of the coolest cloud service if you want to do no code to fully code machine learning. And we're going to walk through on how this workspace works and what can you do with it for the following 2 sessions. And with that, please remember to go to our meetup page where you can check out these sessions and you can sign up and register immediately. And what's coming up next, Gosha?
Yes, so next we create something surprise for you because it's a December. So we're going to show you each day some challenge. So it's kind of advent calendar, but you'll be able to answer some questions and get to know more and check your knowledge about our AI42 sessions.
Yes, and the coolest part of all this is that if you are the best, you might get a little surprise. So with all that, we want to say a big, big, big thank you in the name of AI42 for joining us today. And also would like to thank you again, Terry, for sharing your knowledge with us. And I hope you enjoyed the night today.
Thank you for having me, everyone.
So have a great evening, everyone. Thank you.
Thank you for coming.